Good morning or good afternoon, depending on where you are. We are continuing with our thermodynamics lectures. My name is Professor Duke Orata. I want to look at steady state flow of heat in solids. Always when we are talking of steady state flow, we are thinking of those systems which are kind of uniform. In other words, there's no accumulation of energy or material within the system. So when you talk of steady state flow, then it means that the rate of heat flow in that particular system is relatively constant and the temperature in that system is constant. And so there are several methods with which we can have flow of heat in this system. We'll just look at them briefly. One of them is conduction. And in conduction, it involves molecules. In other words, it involves molecules vibrating about their mean positions and, of course, movement, enhanced movements, as you know from the elements of kinetic theory of things like gases, of these fluids, there is enhanced movement of these molecules. And so there is these movements which are resulting from this molecular activity in this particular system. They are not bulk movements. So these are more of as a result of molecular activity. As a result and so that's why you will see, for example, conductivity in liquids and gases is relatively poor because the molecules are significantly far apart, so they don't quite kind of interact. But in things like metals, so we'll see conductivity is poor in fluids, that is liquids and gases. And this is because of the large separation between the molecules. While in things like metals, we have this huge population of electrons which are free to move from atom to atom, and so you see relatively good conductivity in metals. Electrons, we can move from atom to atom. Therefore, conductivity is significant. It's significant. That's just one mode of heat transfer in systems. The other one is convection. And just like in the case of conduction, in the case of convection, heat will be transferred. Heat will be transferred between a solid and a liquid boundary. And one of the fundamental characteristics that there's normally a temperature differential. In all these cases, there's a temperature differential between those two bodies. There's a temperature differential between those two bodies. So there's the diffusion of thermal energy from region of high temperature to low temperature. So there is normally a temperature differential. Differential between the bodies, the two bodies. That's always fundamental. For heat transfer, there must be a differential in temperature between the two bodies or within that particular system. And so when we're talking of convection, we have talked about boundary between fluid and solid. So the moment the word fluid comes in, where we're talking about fluid, then we'll have to worry about viscosity. We'll have to worry about density. We'll worry about thermal conductivity. Just among a few which we are mentioning. So you have to worry about those. We have to worry about velocity, etc. In other words, when you're dealing especially with liquids, then you have to worry about the continuity equation, which we look at in other lectures. So we can have what we can call forced convection. Here is, for example, where you pump the liquid through a heat exchanger. So you can pump a liquid through a heat exchanger. And now we are familiar with this. If you look at our other lectures, we have talked about compressors and so forth. And so we know that you can actually pump a liquid from region of low pressure to high pressure, using some of those mechanical systems. And then there could be natural convection. Other than forced convection, you can have natural convection, and that will be as a result of the density gradients within that fluid, which will result in movements. So we can have natural convection. This will result from density gradients in the fluid. Finally, there is another form of transfer of heat, which we call radiation. We don't want to focus on that much. Radiation for now. And in this particular transfer, we are going to look at it at the tail end of our discussions. In this particular case, the medium is not critical. So you can have all manner of radiations, electromagnetic, and that could be, we can have infrared, we can have infrared radiations, we can have microwave, just to mention a few. So these are just modes of transfer of heat within systems. And more importantly is we are saying that for steady state flow of heat in systems, it means that the rate of heat transfer is constant and the temperature in that particular matrix is constant at all points. And so there are those matrices we can consider as anisotropic. If you have anisotropic matrices, you can have anisotropic matrices. And we can have isotropic matrices. So this kind from iso, which we have used now quite extensively in our discussions in previous lectures, there is uniformity in the material in all directions. Uniformity in the material in all directions. And in this particular case, there is non-uniformity. So you find in some of those kind of cases that orientation would affect, for example, how heat is transferred in those matrices. Now, we want to look at a very important concept in this particular case for conduction. We look at the Fourier law. Fourier law in terms of this heat transfer process. Fourier law in terms of this heat transfer process. Now, what does it say? When we're talking of Fourier law, we are thinking of solid boundaries which are perpendicular to an axis. For example, let us note, going three-dimensional, let's just think of a simple axis like an x-axis. We want to see heat transfer between solid faces which are perpendicular to an axis. And so if we have, for example, just theoretically, say that this is our x-axis. Let's try to get it better. Let's say this is our x-axis. We are thinking of these solid faces which are perpendicular as a right angle to that x-axis. Let's call that a solid surface. Let's call it a solid surface. And they're perpendicular to that axis. We've taken the x-axis, so that just taken a single axis, so that we make our lives easy. And so what we are saying is, suppose that the difference between these two faces, of course they are not as widely apart, we're talking about distance difference, these two faces, which is, if this is at x and this at x plus dx, so we are talking of infinitesimal separations. Infinitesimal separation, that's a term we have always used and now we are familiar with, that term infinitesimal. That's a term we are now familiar with from other lectures. So if this is x and the other one is x plus dx, and let's say also the temperature difference is just some small amount dt, infinitesimal again. Then Fourier law is as a result of empirical or experimental determination. So the same Fourier law is as a result of empirical determination. And the two observations of the two empirical outcomes is that, one, the heat flux density or the rate of heat flow in that particular system, Q, or rate of heat transfer, Q, is proportional to the area, that surface area involved in the heat transfer, and is proportional to the difference in temperature, but inversely proportional to the distance between them. So that Q is minus K A dt over dx, where K is the thermal conductivity, A is the thermal conductivity, A is the surface area, or is the area involved the process. And of course, dx is that separation or that distance which you have indicated here, x plus dx. That's just the distance, x. Let's call it separation distance. And of course, this is the rate of heat flow, or what we call the heat flux density. This is the Fourier's law, very important for us in our systems. Now, let us just try to work with it and see what we can get from it. Suppose, for example, we assume that, let us call this surface 1, and that is surface 2. And in this surface 1 and surface 2, they're both isothermal, so that the temperatures in those surfaces are uniform. So the surfaces we assume are isothermal. So let's assume the surfaces are isothermal. Assume surfaces 1 and 2 are isothermal. I don't like this pen of mine, it's fading. Are isothermal. In other words, the temperature of that particular surface is uniform. Temperature over the surface is uniform. And also that the rate of flow of current in that surface, the rate of flow of heat in that surface is uniform. Obviously, the word rate of flow of current, we are going to see that actually the rate of heat flow over that unit area can be considered to be like the current, and the difference in temperature can be considered as the potential. So there is electrical and thermal, some relationship. Now, so that's uniform. The rate of heat transfer is also uniform. So suppose we now want to work with this Fourier's law to establish a case where we have these two surfaces, that is 1, and that is 2, and we have them there, and they are separated by some infinitesimal distance. The change temperature is infinitesimal, and let us say that the thermal conductivity K1 for surface 2 and K1, we call it K, is an average of the thermal conductivities of those two surfaces. And let's say that thermal conductivity K is given by, let's say for two parallel surfaces, 1 and 2, with thermal conductivity K equals to A T plus B, where K is the mean of K1 and K2. Let us see what we'll get in this particular type of a system when we use Fourier's law, terms of the heat flux density and those other parameters. So from Fourier's law, you know that from Fourier's law, we can say that Q is equals to minus, we have K there, AT plus B. Remember that is the thermal conductivity. And then we have change in temperature dt over dx. So if you integrate over the two surfaces, we will have q dx, surface 1 to 2. Let's first rearrange them. So let's have q. We have left our area here, forgotten our surface area. Let's just put it there. We know that area. We already know that expression. So we have, so if we rearrange these quantities, q over a, and call that q, that will be a plus at plus b dt over dx. So simple rearrangement and integration. So we just have then q dx from 1 to 2 will be equal to at plus b integral dt from 1 to 2. And of course, this is simply q into x2 minus x1. You already know from all the many lectures you have had that you use the identity dx is simply x plus c. And that integration constant is there if you don't put the limits. Since we put the limits, we don't need it. And so this becomes, that becomes at squared over 2 plus bt to 1. So again, don't forget, we always remind ourselves to the n dx, those identities which use 1, we don't assume anything. We don't assume anything for accuracy purposes. It's very important to always remember things. Don't just assume them. Because when you write them down, then also it guides you. It's very easy to make mistakes when you assume things. Now, so if we proceed with these particular ones, we proceed with these quantities. We have 1, 2. That will, we have already sorted that out. The other one, so we have q x2 minus x1 is equals to a t2 squared over 2 plus b t2 minus a t1 squared over 2 plus b t1. So if we factorize this quantity out, if we factorize this quantity, we can see that we are able to simplify it further in the sense that we will have a over 2 into t2 squared minus t1 squared plus b into t2 minus t1. Using perfect squares to simplify that, we know that t minus 1, yes, we are using that identity there, t2 plus t1 times t2 minus t1, that becomes t2 squared minus t2 t1 plus t1 t2 minus t1 squared. And of course that cancels with that. So we can use this to simplify that by replacing that quantity, this simple one here. Once you identify that identity of perfect squares. So we have q then into x2 minus x1. And so now we just substitute this for this expression is similar to that, so that you have simplified, that you can simplify the whole quantities here because you have T2 minus T1, and you can see it already there, so we'll be able to factorize that. This is perfect square. So what do we have? So that becomes A2 into T2 plus T1 into T2 minus T1 plus B into T2 minus T1. So if we factor them out, then we have Q into X2 minus X1 is equals to T2 minus T1 into A2 over T2 plus T1 plus B. And so we have this expression here. We have this particular expression. We have Q, therefore, can be expressed as T2 over T1 over X2 minus X1 into A over 2 T2 plus T2 T1 plus B. And don't forget, this T2 minus T1, that's a temperature differential, is just can be considered to be the same as electric potential. So this quantity here, you can consider that to be similar to an electric potential. And of course, this Q, don't forget that this Q was Q over A. It's like the electric current. I. That's like the potential E. So thermal transfer and electric current are somehow related. They are somehow related. And our relationship here is, we think of that temperature differential as the potential, and that flow there, that heat flux density per unit area as electric current. So there's some similarity in terms of thermal transfer and transfer of electric current. There's a close similarity between those systems. Points to note. 1, transfer of heat in solids involves molecular activity. The vibration of those molecules within their mean positions is important. And in liquids and in fluids, that is liquids and gases, the distance, the separation between the so-called free path between the atoms or the molecules is too large, so they don't quite interact. That's why you will see that in general, you will find that the conductivity is poor in gases and in liquids. And we have seen convection. We can have forced convection and have natural convection, and because we are talking about fluid, then we have to worry about continuity equation. We have to worry about things like the density, velocity, and viscosity and the likes. And you have seen, talking of radiation, that a medium is not necessary, and we'll look at all those particular systems. And it's very important to also mention to you that in general, when it comes to thermal conductivity, it is normally inversely proportional. Thermal conductivity, okay, it's almost inversely proportional to temperature in the case of, in some metals. And it's not the whole range, and not in the whole temperature range. But you'll see this pattern that as the temperature increases, that value kind of decreases. But it's not in the whole range, because again, you can pick up at the tail end there. So we don't want to be so committed in terms of that. It is subject to the particular material you're dealing with. And like I've said, there's anisotropy, there is isotropy, and all those affect the transfer of heat in terms of the symmetry in those particular molecules, in those particular substances. So let's stop at that particular point. We are continuing with our lectures.